Okay, so now that we've done some sigma notation, we've worked with that a little bit, I want to actually use it and combine the idea of a limit to find this sum here. The limit as n approaches infinity of the sum from I equals 1 to n of 2 plus 3i over n squared times 3 over n. Now, let's remind ourselves of some formulas. We have the sum of a constant. We have the sum or difference, the sum of a sum or difference of two functions. We also have the constant multiple. We can pull the constant multiple out. And then we have these summation formulas. We proved these last year in pre-calculus honors using math induction. Okay, but these are formulas that you do need to memorize. Okay, we've got to memorize these ones. Now, just to help us memorize, if you remember our arithmetic sequences, you had the first term plus the last term divided by 2. In other words, the average of the first and last term times n. Well, if you think about the sum of the integers, I, the first term is going to be 1, the last term is going to be n. Okay, so if we average those, we have the n plus 1 over 2, and then we're going to multiply that by the n. Okay, so that's taken directly from our arithmetic sequence or series formula. Now, the others you're just going to basically have to memorize, but you'll notice these, all three of these have this n times n plus 1, n times n plus 1, n times n plus 1. Here's the curious thing. The sum of the integers is this. The sum of the integers cubed is this squared. See, n squared, n plus 1 squared, 2 squared. Okay? Now, the sum of the integers squared, however, is this. You'll notice we have the n and the n plus 1, and then we have a 2n plus 1. Helps you remember the 2 goes with the squared things added together, and then it's all over 6. Okay, so you can, if you remember them in this order, even though it's not the order of the powers, you go 2, 4, 6 in the denominators. That might be helpful. Okay, so let's actually start looking at the sum that we're trying to find. Okay, so what I'm going to do is I'm going to use some different properties that we have, use these to find the actual value of the sum. Now, first of all, I'm going to deal with this, and then I'll take the limit, just so I don't have to write the limit over and over again. And you'll notice here, I'm taking the sum from I equals 1 to n. The n here, even though it's unknown, or we can make it whatever we want, we're actually going to treat that as a constant as we do the sum, because the variable of the sum is I. So that means 3 over n is actually going to be a constant, and I'm going to pull that out here. And that's the sum from I equals 1 to n now of 2 plus 3i over n squared. Okay, now, I still don't have anything I can really work with too well, so what I'm going to do at this point is I'm actually going to FOIL and separate this into three different sums. So the 3 over n is still hanging out here, but I'm going to have the sum from I equals 1 to n plus the sum from I equals 1 to n plus the sum from I equals 1 to n. And you might say, well, where are those three coming from? Well, that's from foiling the 2 plus 3i over n squared. So the firsts are a 4, then I have a 6i over n plus another 6i over n. That's going to be a 12i over n. And then the 3i over n squared is a 9i squared over n squared. Okay, so at this point, we again can see a constant multiple in some of these. Okay, 12 over n is a constant multiple. So I'm going to pull that out, and now I have the sum from I equals 1 to n of just the i's, and that we have a formula for. Here, 9 over n squared is a constant. That's from I equals 1 to n of I squared. Okay? Now, the first one is just a constant. And we learned the rule, it's just 4 times n, because we're adding 4 plus 4 plus 4 n times. Okay. So, now we have this. And now I need to do a little bit more simplifying. So this 3 over n is still hanging out here. We now have the 4n plus 12 over n times the sum of the i's is, as we just saw, n times n plus 1 over 2. Okay. And that will simplify a little bit. We also have a plus 9 over n squared, and the sum of the squares by our formula is n times n plus 1 times 2n plus 1 all over 6. Okay? Now, at this point, I'm going to simplify everything as much as I can. Still not distributing this yet, but I have a 4n plus, and then we have this. So look, the n's cancel, and the 12 over 2 is 6. So that's going to be 6 times n plus 1. And then here I've got an n over an n squared, so that's going to leave just an n in the denominator. 9 over 6 is 3 over 2. And I've got a 2n squared plus 3n plus 1 when I FOIL those parentheses. Alright? So I'm going to keep going. There's more we can simplify. 3 over n times 4n plus 6n plus 6 plus. Now, this I'm going to split into 3 separate fractions. Okay? That is 6n squared over 2n plus 9n over 2n plus 3 over 2n. And you can see those would simplify. I've got a 3n plus 9 halves plus 3 over 2n. Okay? Okay, so now I'm going to simplify a few things, and that'll allow us to then distribute the 3 over n. So 4 plus 6 plus 3, that's 13n. 6 plus 9 halves. 6 plus 9 halves is going to be 21 halves. And then that's a 3 over 2n. And I am multiplying that by 3 over n. Now notice here, when I do that, I'm going to have 39, and the n's will cancel out, plus 63 over 2n, plus 9 over 2n squared. And that is finally simplified. That's a lot of work. But notice, now that I have that, this is going to equal the limit as n approaches infinity of 39 plus 63 over 2n plus 9 over 2n squared. And you know, as the limit as n approaches infinity, n's approaching infinity, we can look at it in terms of horizontal asymptotes. So 39 just stays 39, but if the n's on the bottom, 63 over 2n is going to approach 0, and 9 over 2n squared is going to approach 0, so this whole thing just equals 39. Alright, so now that we've seen that done once, one thing I want to do here is I want to look at a problem here of kind of where we're headed with all these sums. And to do that, I'm actually going to look at the area bounded by a function, a curve, the x-axis, x equals 2 and x equals 5. Okay, so here's a drawing, and I copied this 3 times here, right? Here's a drawing to illustrate what we are trying to find. I'll zoom in a bit here. And you'll notice the area I want is this shaded in area. And you can see here the 4 boundaries that we were given. We were given the function y equals x squared. We were given the x-axis. Okay, so here's y equals x squared, the x-axis, x equals 2, so that's a vertical line, and x equals 5. That's another vertical line. Now, this is kind of the shape of a trapezoid, but it's got a curve. All right. If this were, straight along here, then we'd have a trapezoid, okay? But we need a better way to approximate the area here, okay?
It's like all the y values.
So,
0 to 5.
I'm sorry, what?
It's like all the y values from 0 to 5 and add together.
Yes, it's all of these y values. It's not just the ends. We don't just connect it with a straight line and make it a trapezoid. We have to actually follow the curve along x squared, okay? So the problem is this curved side. How do we find the area when one of our sides is curved? And right, at least to begin with here, the best thing we can do is approximate, okay? Is approximate. Now, we have what are known as Riemann sums, okay? And I want to introduce this idea, first of all, with what's called the right or upper Riemann sum. Now, it's called upper when we have a function that's increasing, okay? And let me show you what I mean by this. So let's suppose that I were to take this shape and divide it into 3 evenly spaced parts. All right, so since the total width here is 3 units, I'm going to cut it here at 3, at 4, and then of course at 5. All right, is the end. And what I would do here is I could take then and make a rectangle. And I know how to find the areas of rectangles. But I'm making the side of my rectangle be where the right-hand side of the division I made hits the function. Okay? Now that's why this is called the right Riemann sum, because I'm using the right sides of the rectangles to find my heights. Okay? Because if you think about it, all right, because I made 3 rectangles, how wide is each one of them? 1 unit, okay? So this rectangle, this rectangle, this rectangle, they're all 1 unit apart, 1 unit wide. Okay? Now, how tall are they? What'd you say? X squared, okay? Now, the key is, what x are we using? Well, right here, what's the x coordinate?
What's x squared?
The whole function, the curve here is x squared. At this point right here, what is the x coordinate? 3. So how tall is this rectangle? 9, okay? So this point right here is the point 3, 9. So that rectangle is 1 by 9. Okay? Let me actually write it on the inside. Okay? So that's 1 by 9. So what's the area of that rectangle? 9. Okay. So that's 9. Now the next one. The next one here, if I look at the point where the corner of the rectangle meets the curve, what's the x coordinate there? 4. So that point is 4, 16, so the height of the rectangle is 16. So what's the area of the rectangle?
16.
16.
Oh, so the y coordinate is just the area?
In this case, yeah, because they're each 1 unit wide.
Okay.
Alright? What's the point up here?
525.
525. So the height of that rectangle is 25, the width is 1, so the area is 25. So if I add those together, I get 50 square units, whatever the units are here, as my area. Okay? Now question, is that an accurate estimate of the area?
No.
Why not?
It's bigger than the.
It's a curve.
It's bigger than the actual, right? Because I'm including stuff here and here and here that I'm not supposed to, right? So this area is too big. Okay? Now, let's try it if I did it the other way. This is called the left or lower Riemann sum. Let's say I divided it up into 3 parts again, but this time, for the height of the rectangle, I made it where the left side of the rectangle hit the function. So in this case, that's going to be one of my rectangles. This is going to be one of my rectangles. And this is going to be one of my rectangles.
It will be smaller than the actual.
Okay? The area that I get with these 3 rectangles is going to be what?
Small.
It's going to be too small because here I'm actually missing out on this whole piece, this piece here, and this piece there.
Oh, I see.
Okay?
So
But guys, the process is going to be the same.
you use the first one, subtract the area of the second one, and then add up the
And then
subtraction part and sum with the second one.
You're on the right track. You're on the right track with that, but let's go ahead and find the area here first, and then we'll tackle how to get an accurate estimate here. Okay? So that point there is the point 24. This point we already had was 39, and this point here was 416. So what are the areas of our 3 rectangles if they're each 1 unit wide? 4, 9, and 16, okay? So 4, 9, and 16, we add those up, and in this case we get 29 units squared for our area.
Okay.
Okay?
wait, what did you? Oh, okay. You just said.
Alright. So, that obviously we already said is too small. We're missing some. How could we get a better estimate though? We got one that's too big, one that's too small. What are some options? Melissa?
You choose the point.
Okay, if we average those two together, if we found the middle of those two, 50 and 29 would be 79, so like 38 and a half. That would be an approximation that might be closer to what the actual area is. That's a good idea, okay? In fact, there's another method here where we actually, instead of using the left or the right hand side, we use the middle. Okay? We make the top of the rectangle be the middle of the range. Okay, and that essentially is what we would get if we found both of these and averaged them. Okay? What's another way though?
Like
Subtract.
like the equal, like each rectangle smaller, like as smaller as possible.
Okay, if we made each rectangle as small as possible, as Angel said here. Okay, let me get another copy of that picture here. Okay. Let's say that instead of just 3 rectangles, let's say, for sake of example, I made 6. Okay? So 1, 2, 3, 4, 5, 6. All right, so in this case, they're only half a unit wide, but notice we can do the left hand again. So there's one rectangle, there's another rectangle, there's another rectangle, there's another rectangle, there's another rectangle, and there's another rectangle. Okay? Now you'll notice I'm still missing some. Okay?
So you make it to infinity.
Aha. If we made the number of rectangles approach infinity, that would minimize, because notice here, the pieces that we're missing are much smaller, even just going from 3 to 6 rectangles. Okay? Even just dividing it from 3 to 6 rectangles, the amount of area that we're missing is much, much less. Okay? So, yes, we want the number of rectangles to go to infinity. And that's where this is taking us, okay? We just saw this. The actual area of the region is going to be somewhere between this, which we call the lower, and this, which we call the upper rectangles, okay? Now notice here how this example is slightly different because it's not constantly increasing. All right, look at this here. On some of these rectangles, the left side is hitting the function, but on some, the right-hand side is hitting the function. That's why when we have something that's not constantly increasing or decreasing, we just call it the lower and lower or the upper rectangles. Okay? So, the actual area we're looking for is somewhere between those. Okay? Now, going back to our example, let's actually do what Jason mentioned there and let the number of rectangles approach infinity. Okay? Again, remember we were dealing with f of x equals x squared, and we were on the interval from 2 to 5. Well, that interval is 3 units long. And if n is the number of rectangles I want, I'm going to have to divide 3 by n, right? Right? Okay? So that is how wide each of the rectangles is going to be. So as I'm looking at area equals, length times width, I know all of these are going to be times 3 over n for the width. The height is going to be a little bit different because I'm starting at 2, and then for each rectangle I've got to add 3 over n to get to the other side of the rectangle. So once we get to the other side of the rectangle, we're going to evaluate the function at that value, and that will tell us the height. So the first rectangle will actually have an area of 2 plus 3 over n evaluated at f. That's going to be its height, and it's going to be 3 over n wide. So it'll look like this. The function will be coming through something like that. All right, but it's going to be 3 over n wide, and the height of it is going to be whatever f of 2 plus 3 over n equals. Okay? So, that is for these right upper sums. Okay? Now, you'll notice here there's an I in here, and that's because once I do the first rectangle, I've got to go over another 3 over n to make my second rectangle. Okay, so after the first rectangle, I'm going to be adding 3 plus 3 over n once, the second rectangle will be twice, third 3 times, and so on. So that's how we get the right upper sum. And then what I'm going to do is I'm going to add up all of those areas. So the area is f of 2 plus 3 over n times that width 3 over n. Now, for the left or lower and lower Riemann sums, if I'm doing the same idea here, but I want to have my rectangle have a width of 3 over n, but I want the height of it to be hitting the function on the left side. Notice I'm starting at 2 for the first one, and then it's going to have a width of 3 over n, so that's going to be 2 plus 3 over n. That comes up here, and then that's my second rectangle, and so on. Okay. So you'll notice here, instead of just the 3 over n being multiplied by I right here, it's actually times I minus 1, and that's because for the first rectangle, I don't want to add the 3 over n yet. I want to stay at 2. And for the height, I want to evaluate the function at f of 2. Then for the second rectangle, I'm evaluating it at f of 2 plus 3 over n. Okay, so that's why we have this I minus 1 here, in order to make it so that we don't add the 3 over n the first time, we just do it, and that keeps us on the left side of those rectangles. But again, you can see the area for the left side, the area, I'll switch colors here, the area is f of 2 plus 3 over n times 3 over n, and that's the area of that first rectangle right here. Okay, so both of these formulas right here, this is for the first rectangle right here, and this one is for the first rectangle using the left side. Okay, now if we generalize this, the interval that we had was from 2 to 5, but let's say that we're doing a function f of x. We want the area under f of x over the interval from a to b. Okay, it actually doesn't matter if it's a closed interval or an open interval. The interval from a to b. We typically just use a closed. What we're going to do in this case, to find the width of the rectangle, we took the right-hand side of the interval minus the left-hand side, 5 minus 2. So in this case, our width is going to be b minus a. And I'm going to divide that by however many rectangles I have. That's going to give me the width of one rectangle. Okay? Now, when I find the area, okay, I'm going to take that width, b minus a over n, and I'm going to multiply it by the height of the rectangle at that point, which is going to be f of what? Well, I'm going to be starting at a, and I'll do the right hand one this time. So it's f of a plus b minus a over n. Okay, so that's again the right and upper sum that I'm finding the area for. Okay. Now, putting this together, what are we actually doing? Okay. You'll see the notation down here. What we're actually finding here is what's known as the definite integral. You have the elongated s here we saw with our antiderivative or our integral. The definite integral means we have definite values that we want to integrate from and to. In other words, we have that interval from a to b. Okay? So what we're doing here is we're going to take the limit as the number of rectangles approaches infinity. So the width of the rectangle is going to get smaller and smaller and smaller as we get more and more and more rectangles of the sum of the areas of the rectangles. And you can see here, we did the same thing that we did with the right-hand side up there. We've got the width of the rectangle, b minus a over n, times the height of the rectangle, which is f of our left side of the interval plus the width times however many rectangles we've done already. Okay. So that is our formula for a definite integral on an interval from a to b.